Now let's see how to generalize the singular value decomposition to non-square matrices. Suppose that you have a rectangular matrix A having the dimensions of n multiplied by n. So you have m rows and n columns, something like this. For example, 1, 2, 3, 4, and maybe 2, 3, 2, 4, and maybe 2, 4, 6, 8, for example. So this is a 3 by 4 matrix. And I want A to be equal to U sigma V transpose. Now, what are the dimensions of those matrices U, sigma, and V? I still want the matrices U and V to be orthogonal square matrices because those square matrices have very nice properties and we will use them extensively as we develop further from the singular value decomposition. So we still want those to be square orthogonal matrices. We also need the matrix sigma to be a diagonalized representation of the matrix A. So if we have AX equal Y, then we still need U sigma V transpose X to be equal to Y, which means that we want that U transpose Y to be equal to sigma multiplied by V transpose X. So I want sigma to be a good representative for the matrix A. So I need sigma to have the same dimensions as the matrix A. So if the matrix A was an m by n matrix, I need this to be a square matrix, so this must be m by m. I also need this to be a square matrix, so it will be n by n. And so this matrix sigma must be an m by n matrix, so it must have the same dimensions as the matrix A right here. Very well, now what are the vectors inside this matrix U right here? Originally, for the square case, matrix U had columns from the column space. We see that for this rectangular matrix right here, this dimension is m. So every column has m components, and so we have m independent vectors in the m dimensional space representing the column space. For this specific matrix, for example, if we could have 3 independent columns for the column space, then all the columns of the matrix U will belong to the column space. Unfortunately, this is not the case right here because this row right here is dependent on this first row, and so the number of independent columns is actually 2. So this matrix will have 3 columns, 2 of them will belong to the column space and the third one will belong to the left null space of the matrix A. Now for this matrix V, this matrix B will be an n by n matrix because every row has n components. The number of components for every row is equal to the number of columns n. Again, for this specific case, we have 4 components, and so this matrix will be a 4 by 4 matrix. 2 of those rows of the matrix V transpose will belong to the row space, and the remaining 2 rows will belong to the null space of the matrix A. Note that the rows of V transpose are the columns of the matrix V, so the matrix V will have 4 column vectors. The first 2 columns of the matrix V will belong to the row space of the matrix A, and the second 2 columns of the matrix V will belong to the null space of the matrix A. Let's now see what would the matrix sigma look like. We have the following scenario. We have A multiplied by V. V is a 4-dimensional matrix, a 4 by 4 square matrix. So we have here V1 and V2, which is equal to VR. Then we have V3 and V4, which belong to the null space of the matrix A. Now this is equal to some matrix U, which is a 3 by 3 matrix. It has only 3 columns, U1, U2, and U3. Then this is multiplied by a matrix that has the same dimensions as the matrix A. So here I have sigma 1, 0, 0, 0, a 4 by 3 matrix. Then here I have 0, sigma R, 0, 0. Then I'll have the third row, 0, 0, 0, 0, to have the same dimensions as the original matrix A. Now let's see whether this is still valid or not. We have A multiplied by V1 to be equal to sigma 1 U1 plus 0 multiplied by U2 plus 0 multiplied by U3, and this is equal to sigma 1 U1. So this is good. A vector in the row space gets mapped to some vector in the column space. Now A V2 is equal to sigma R U R. So this is VR, this is VR, and this is UR because the rank is 2. Both the column rank and row rank must be equal to each other. So we have AVR is equal to sigma RUR. Now for the remaining vectors, those belong to the null space. So AV3 should be equal to 0. And indeed here we have 0 multiplied by U1 plus 0 multiplied by UR plus 0 multiplied by U3. So this will be equal to 0, which is equal to 0 U3, and also AV4 is equal to 0, which is equal to 0 U4. So this worked for this case where the matrix was a rectangular matrix with the number of rows less than the number of columns. Now let's cover the final case where the matrix A is a tall matrix like that. So I might have 4 components here, 1, 2, 3, 4, and then 2, 2, 2, 2, and then I might have 4, 4, 4, 4. So the rank is still 2 in this situation. Now this is a 4 by 3 matrix. So the dimension of every vector in the row space or the null space is equal to 3. So the matrix V is a 3 by 3 matrix now. So here we have A multiplied by the matrix V, which is V1, VR, V3. This is equal to the matrix U, which has columns from the column space and the left null space. So we will have 4 columns, 4 bases for the complete 4D space, U1, UR, U3, and U4, and this is multiplied by some tall matrix sigma that has the same dimensions as the matrix A. Here I'll have sigma 1, 0, 0, 0, sigma R, 0, and then 0, 0, 0, 0, 0, 0, because I want this to be a 4 by 3 matrix. Now again, AV1 is equal to sigma 1 U1 plus zeros elsewhere. AVR is equal to sigma R UR. Now for AV3, we have that AV3 is equal to, here I have 0 multiplied by this plus 0 multiplied by this and so on. So I will have this equal to 0, which is correct since V3 belongs to the null space of the matrix A. So again, there is a valid singular value decomposition for the matrix A when the matrix A is a tall matrix. So in general, for any matrix, singular or not, square or not, we can always have A to be equal to U sigma V transpose, where this is an orthogonal square matrix, this is an orthogonal square matrix, and this is a diagonal matrix or a nearly diagonal matrix that has the same shape as the original matrix A. In the next video, we will finally talk about how to calculate those matrices, how to get the matrix U, the matrix sigma, and the matrix V.